So, Neuvillette, have you ever heard of data processing pipelines? They're quite fascinating.
Oh, tell me more, Hu Tao. I'm intrigued by any system that processes information efficiently.
Picture this. Data processing pipelines are like assembly lines in a factory for information. They take raw data, process it through various stages, and produce refined, useful data at the end.
Interesting. And you mentioned their operational frequencies vary. What does that mean exactly?
Ah, yes. These pipelines can operate in different time frames. Some run only occasionally. Those are periodic pipelines. Others, they never stop and are called continuous pipelines.
I see. And does each type have its own specific challenges?
Exactly. Periodic ones might struggle with bursts of activity, while continuous pipelines require constant resource availability and monitoring.
Resource availability sounds crucial. Could this lead to operational problems?
Yes, indeed. Imagine a factory suddenly needing more electricity than it can handle when all the machines are on. Pipelines can face similar issues, resulting in delays or crashes if not well managed.
That makes sense. How do you maintain stability in such systems?
Well, there's a clever approach known as the leader-follower model. It helps balance workloads across the system to prevent any one part from becoming overwhelmed.
Leader-follower model, you say? Sounds strategic. How does it improve upon the existing pipeline structures?
The leader-follower model enhances both reliability and scalability. It designates one process as the leader to manage tasks while followers execute them. This distribution of responsibilities keeps things smooth and steady.
Reliability and scalability, essential qualities especially when dealing with vast amounts of data, like in big data scenarios.
Absolutely. Big data comes with immense volumes and complexities. These qualities ensure the system can handle that scale without buckling under pressure.
It seems big data adds another layer of challenge. How significant are these difficulties compared to traditional data management?
Very significant. Traditional methods often fall short due to the sheer size and speed of big data. With pipelines, you need models that offer enhanced oversight and adaptability.
Enhanced oversight. Does that require more sophisticated technology or protocols?
Indeed. Sophisticated technology and robust protocols ensure pipeline systems remain agile and responsive, even as data demands evolve.
Tell me more about the adaptability you mentioned. How does a pipeline adjust to changing data flows?
Pipelines adapt through modular stages. If one stage encounters changes in data flow, it adjusts its processing methods, ensuring the entire pipeline remains functional and efficient.
That flexibility must combat the unpredictability in data sizes and processing speeds, correct?
Precisely. With big data, you never quite know what data storm might hit next, so being able to recalibrate on the fly is invaluable.
Fascinating. I've always believed in the power of adaptability, even in legal systems. A dynamic framework should be a cornerstone of any efficient system.
I agree. Adaptability is key. It's what makes data processing pipelines a persistent force, evolving with technology and data expectations.
And the leader-follower model, you said it was proposed as a more reliable alternative. Is it widely adopted yet?
It's gaining traction. Organizations that deal heavily with big data are seeing its benefits because it streamlines the process and mitigates risks.
Mitigating risks in data processing. It sounds akin to safeguarding the rule of law. Each detail matters, and systemic oversight is crucial.
Exactly, Neuvillette. Just like ensuring justice is served properly, consistent attention and strategic planning keep pipeline operations efficient.
I see the parallel now. It's about creating frameworks that are resilient under pressure, while still delivering desired outcomes.
Exactly. That's the magic of these data processing pipelines and their evolving methodologies.
I'm quite inspired to learn more about these systems. What more can you share about data complexities and their management? Hu Tao, I appreciate all the insights you've shared so far. I'm curious now about the origins of data processing pipelines. Where did this ingenious concept come from?
Ah, the history of pipelines. They're quite the evolutionary tale. Originally, the design started from very simple programs that transform data in straightforward ways. Picture early computing, where a program read data, made changes, and output the results.
Interesting. So were these initial pipelines just singular processes without much complexity?
Exactly, Neuvillette. These were simple pipelines, often managed by scheduling tools like cron. They operated as single-phase pipelines, performing one task at a time.
I can see how that worked for smaller data sets. But what happened as data grew, especially with the emergence of big data?
That's when things truly started evolving. Big data brought datasets so vast and complex that traditional methods couldn't keep up, forcing a shift from simple to what we call multi-phase pipelines.
Multi-phase pipelines, how fascinating. How do they differ from the simple ones?
Multi-phase pipelines are like chains of these simple programs. Each program is a phase, handling a part of the data processing sequence. As you can imagine, the more phases in a chain, the deeper the pipeline.
Pipeline depth, so that's a measure of how many processes are linked together.
Precisely. You could have a pipeline just one program deep, or it could include tens or hundreds of interconnected programs, each with specific tasks, depending on the complexity needed.
And I suppose the depth relates directly to the challenges and ease of managing large data sets, particularly within significant data environments like Google.
Absolutely. With big data, it's like putting together a complex puzzle. Each phase must handle a portion of data efficiently to avoid bottlenecks and errors.
I can sense the challenges already. Were there historical techniques or technologies that inspired these modern pipelines?
Oh, definitely. The concept harks back to things like coroutines, DTSS communication files, and Unix pipes. Each of these contributed foundational elements to the pipeline philosophy.
So these historical techniques laid the groundwork for the pipelines of today. Amazing. How did they adapt to the increasing complexity?
Exactly. The complexity called for a more methodical approach, hence the multi-phase setup. It was all about ensuring each data chunk was carefully transformed and passed down the line.
A methodical transformation. Does this mean more sophistication was needed in pipeline technology as data grew?
Yes, indeed. The sophistication was necessary to maintain accuracy and efficiency. Technologies like MapReduce and Flume played pivotal roles in refining these processes.
MapReduce and Flume, they manage the orchestration of these phases within the pipeline.
Precisely. They provide frameworks to seamlessly manage tasks across distributed systems, ensuring each piece of the data puzzle fits perfectly.
Fascinating. So the evolution from simple to complex pipelines was driven largely by the necessity to handle these enormous and intricate data sets. What other changes did this evolution trigger?
Well, the need for reliability and scalability skyrocketed. New models had to incorporate these qualities to ensure data isn't just processed, but processed well, even when the data scales up dramatically.
And how do framework solutions like MapReduce address these new necessities?
They help by distributing data transformation tasks across many machines, ensuring each task can be processed independently, which is crucial for managing large-scale data.
That sounds quite efficient. But what about the coordination? How do these individual tasks come together without a hitch?
Strong orchestration and synchronization protocols ensure tasks are coordinated properly. Each machine knows what to do and when, minimizing the risk of overlapping or dropping tasks.
So meticulous coordination is key to handling data at this scale, and this framework sets the operational rhythm for data pipelines.
You've got it. It sets everything in motion smoothly. With that, you get consistently fast data processing without hiccups, even when new data storms roll in.
Remarkable. And these advancements allow pipelines to scale proportionally with data growth, right?
Yes, Neuvillette. Scalability is built in, so as the pipeline depth adjusts or the data volume grows, the system holds steady.
Incredible, Hu Tao. These systems truly seem like the backbone of modern data management, ensuring flow and stability in vast seas of information.
They really are like the heart of data ecosystems, pumping vital information where it needs to go, with a rhythm timed to the beat of today's data needs.
And I imagine, as with any living system, adaptability and resilience are woven deeply into their design.
Exactly. Those qualities are precisely what keep data pipelines and the decisions we derive from them alive and thriving.
So as we delve deeper, What other developments or transformations have occurred in the realm of data processing pipelines?
Oh, there's plenty more. The real excitement comes from how these developments continue to innovate and respond to ever-emerging data challenges. Ready for the next deep dive?
Absolutely, Hu Tao. I'm eager to learn more about how these sophisticated systems continue to evolve and influence data processing. Hu Tao, the more we talk about data processing pipelines, the more I see how intricate they are. But I've heard of challenges associated with periodic pipelines, especially when they're in distributed environments. Could you shed some light on these difficulties?
Absolutely, Neuvillette. Picture this. Periodic pipelines are like a scheduled task that occurs at specific intervals. But there are quite a few bumps they can hit along the way, especially when spread across a distributed environment.
It sounds like coordination might be one of those bumps. How do periodic pipelines handle work distribution across multiple systems?
That's one major issue: uneven work distribution. Imagine trying to balance a seesaw with uneven weights on both ends. Some chunks of data might require more resources than others, leading to bottlenecks or uneven processing speeds.
I see. And this imbalance, it could be exacerbated by the very nature of distributed systems, right? Where different machines have varying capacities.
Exactly. And if some machines finish their tasks faster, others might lag behind, causing delays in the overall process. This leads to what's known as the hanging chunk problem, where progress is held up by the slowest task.
A bit like traffic on a highway slowed down by a single obstruction. So how do these pipelines monitor such discrepancies?
Monitoring is another tricky area. Periodic pipelines often lack real-time insights, only collecting data after a task is done. This means if something goes wrong midway, it's invisible until it's too late.
That sounds like it could complicate timely interventions. Are there any common pitfalls or oversights that contribute to these monitoring challenges?
Yes, indeed. The classic trap is not having real-time telemetry. Without it, engineers can't respond to problems as they unfold. It's like trying to navigate through fog without a compass.
And does the systemic strain increase with the growth of data or the number of tasks?
Absolutely. Larger data demands can exacerbate the thundering herd problem, where too many workers start tasks simultaneously, potentially overwhelming the system.
Quite an apt name. It conjures the image of a stampede. Is retry logic a contributing factor here?
Yes, it is. If retry logic isn't set up correctly, it can lead to repetitive strain. Tasks might restart unnecessarily, blocking resources repetitively and compounding the original issue.
I imagine managing these retries would require precision. What about human intervention? Does it play a role in exacerbating these strains?
Indeed, it can. Sometimes engineers, desperate to meet deadlines, may add more workers hastily or without proper adjustment, inadvertently leading to further stress on the infrastructure.
It seems that strategic planning and foresight are crucial. What solutions exist to address these myriad issues?
One promising solution is transitioning to continuous pipelines, which are designed to run perpetually, processing data as it arrives, thereby smoothing out spikes and reducing load issues.
Continuous pipelines, do they handle resource allocation more effectively then?
Indeed, they do. By processing data in near real time, these pipelines can better distribute workloads across available resources, mitigating the sudden spikes seen in periodic models.
And I assume continuous pipelines have advanced monitoring capabilities to catch issues early on.
Spot on. They employ real-time monitoring, which allows engineers to immediately detect and address problems before they escalate.
This must make continuous pipelines a more stable choice, especially for ongoing data requirements. Are there any trade-offs or challenges inherent to their implementation?
While continuous pipelines offer many advantages, they require a solid infrastructure to handle constant data flow and might need higher initial investments in technology and skills.
Investing in the right infrastructure. It seems like a wise strategic move, especially with growing data demands. Is the adoption of continuous pipelines steadily increasing?
Yes, more organizations are recognizing the advantages of continuous pipelines for their reliability and efficiency, particularly in data-heavy industries.
That's a significant shift. With continuous pipelines reducing many issues, do you think they'll become the primary choice in data processing soon?
I do believe so, Neuvillette. As data needs evolve, continuous pipelines will likely become more of a standard, akin to how certain reliable practices naturally shape their industries.
This evolution echoes the natural progression of technological solutions, ever adapting to growing complexity and remaining robust under increased demand.
Absolutely. It's a fascinating journey of adaptation, ensuring data pipelines continue to meet the demands of our data-driven world.
Truly intriguing, Hu Tao. I appreciate the depth of understanding you've shared. As we continue exploring, I wonder about the specifics of how continuous pipelines seamlessly integrate into existing systems.
Integration is an art, Neuvillette. It's about aligning the new with the old so they work in harmony, kind of like composing a new melody using familiar notes.
What a beautiful analogy. I'm curious to hear more about this next harmonization in data processing.
I'm glad you're enjoying the tune. Let's dive deeper into how these integrations orchestrate such symphonic results in data management, ensuring nothing is out of tune.
Hu Tao, I've been pondering the intricacies of these data processing systems you've been explaining. I've heard there's something called Google's workflow system. Could you elaborate on that?
Absolutely, Neuvillette. Google's workflow is quite a marvel. It's designed for continuous data processing, with a focus on reliability. It forms a backbone for managing massive data tasks smoothly.
Continuous processing seems quite different from the periodic pipelines you've previously mentioned. How does workflow manage to handle such vast scales reliably?
Great question. Workflow utilizes a clever design pattern known as the Model View Controller. This pattern is instrumental in managing large-scale data operations effectively.
The Model View Controller pattern, that's fascinating. How is it adapted for handling data at such a massive scale?
Well, think of it this way. The model in workflow is the task master, which holds job states in memory for speed. The view consists of the workers who continuously update the system's state, while the controller can assist with additional operations.
So the model stores data states, and the workers are essentially the active components processing those states.
Exactly. The workers take tasks from the task master, process them, and produce outputs. They can be scaled or replaced easily, maintaining efficiency and flexibility.
I see. This must allow for a great deal of scalability and fault tolerance. But how does this system ensure correctness and reliability, especially during failures?
That's where its robustness really shines. Workflow guarantees correctness through multiple mechanisms. For instance, it employs exactly once processing semantics, ensuring tasks don't get duplicated or dropped.
Exactly once semantics. That sounds quite sophisticated. How is this consistency achieved?
Through unique identifiers and leasing systems, Neuvillette. Each work unit is handled uniquely, and leases ensure only one worker processes a task at given time.
Fascinating. But what if there is a failure or a misconfiguration within the taskmaster itself?
Great point. Workflow has a safeguard. It embeds a server token in each task's metadata. This verifies the identity of the taskmaster in every operation, preventing rogue configurations from causing havoc.
Impressive. So even amidst changes or network issues, the system maintains its coherence. What additional measures are in place for overarching system reliability?
Workflow doubles down on its correctness guarantees. Each task has a unique ID and the system versions all tasks. If a task updates, it replaces the old with a new unique task ID.
And these unique identifiers prevent old errors from cascading into new processes. Ingenious. How does workflow manage resources across different data centers, especially in the face of environmental challenges?
To counter environmental unpredictabilities, Workflow uses Spanner for storing journals, which makes it globally consistent. Chubby, a distributed lock service, aids in electing the lead writer and ensures transactional integrity.
Incorporating Spanner and Chubby must enhance its resilience significantly, especially against disruptions like data center outages.
Exactly. With these systems, Workflow maintains business continuity even if faced with total data center failures or other global issues. Tasks are preserved and picked up by other resources seamlessly.
And this ensures that even if one data center fails, data processing continues elsewhere without a hitch.
You've got it. The system can automatically redirect workloads to maintain steady operations under virtually any circumstances.
Such levels of resilience and correctness really make workflow a potent tool for modern data environments.
Exactly. These qualities enable it to manage and derive insights reliably from big data, addressing challenges that periodic models might falter under.
It's reassuring to know that we have such systems fortifying the foundations of data management. I'm curious, though, does this mean continuous pipelines are set to become the prevailing choice over periodic ones?
Absolutely. As businesses require up-to-the-second data insights, continuous pipelines like workflow will become the norm due to their superior reliability and efficiency.
I can certainly see why. The emphasis on continuous, reliable data flow mirrors the principles of steady governance and ensuring justice and order remain consistent.
Well said, Neuvillette. Like governance, data systems need solid checks and harmonized flow, and workflow ensures that in the ongoing dance of data.
Thank you, Hu Tao. This discussion has been as deep as it is enlightening. I feel far more prepared to appreciate the workings of such complex systems now.
I'm glad to hear it. It's always a pleasure sharing these stories of technological brilliance, a marvel of modern innovation, just like law and order, echoing the balance and precision in nature.